Graph the following piecewise defined function. Indicate whether the endpoints of each piece with a closed or open dot are included on the graph. Well, anytime I approach the graph of a piecewise defined function, what I like to do is to consider it as two separate functions that have restricted domains. So for instance, the first function, which has the graph 3x plus 5, that's just a straight linear equation in the form y equals mx plus b, where m is of course the slope, and slope is defined as your rise over your run, and b is your y-intercept. So we have a y-intercept of 5, so there's 5. We have a slope of 3, so that means my rise over run is 3 divided by 1. So I would go up 3 units, so 1, 2, 3, and over 1 to get to the next point. If I go up 3 more, I'm out of my range. So another thing I can do is instead of going up 3 and over 1, I can also go down 3 and back 1. And notice I'm still on the same line. So down 3, back 1, down 3, back 1, and I'm just going to put in as many as I can fit on my chart. Okay, now here's the thing. This graph is only defined where x is less than or equal to -3. So here's -3. And, I'll put a open circle there because it's not less than or equal to, as I accidentally said. Here's where x is -3, and here's where it's less than that. So my line is only defined from this point right here going this way. So only things on this side of the green line are actually defined. So instead of my line looking like this, which would be just the line itself, instead, what it looks like is there's an open circle here. Get rid of that point so it looks better. And my graph continues this direction. So it's only defined on this part. So from here forward, the line does not exist because we're restricted to where the x values are less than -3. So we'll remove that portion. And none of this stuff was actually part of the graph, so I'm going to go ahead and remove it. And then we'll work on the next portion. Okay, so the next line we have is 1 plus 1/3 x. So that means I have a y-intercept of 1 and a slope of 1/3. So a slope of 1/3, the rise is 1, and the run is 3. So 1, 2, 3. There's another point on that line. Up 1 over 3. And we just keep repeating this to where we can get all the points we can on this line. Also, we can go the other direction as well when we run into one side of the graph. So we can go down 1 and back 3 instead. The reason we can do that is 1/3 is the exact same value as -1 over -3 because the negatives cancel to a positive. So anyhow, down 1, back 3, down 1, back 3. So here is my line. Now if I was going to draw in the line, it would look just like this. But this line is only defined for values where x is greater than or equal to -3. So from this point right here, this way on the x-axis, only in that region is the line defined. So this stuff back here, as far as we're concerned, doesn't exist. So let's get rid of it. Make this look proper. Okay, so my line, I believe I had a point right here, starts right there and only exists when x is bigger than or equal to -3, so just that portion. So none of these points exist on the line either. And that right there is the graph of my piecewise defined function. And all a piecewise defined function is a function that that's joining multiple functions together in such a way that we end up with a function in the end. Because right here, this would not be a function. It doesn't pass the vertical line test. So here's a vertical line that crosses this graph more than one point. So in order to make sure this is a function, it has to pass the vertical line test, which is why that doesn't exist. And that doesn't exist because now it would pass a vertical line test at every point. So you have to consider the restricted domain. But other than that, you're simply graphing a function as you would normally, but then in the end, restricting the domain.